this video, we are going to prove the Rouche's theorem, which states that if f of z and g of z are analytic inside and on a closed curve C, and if absolute g of z is less than absolute f of g on C, then f of z plus g of z and f of z has the same number of zeros inside of C. So to prove this formula, to prove this theorem, we have to let capital F of z to be equal to g of z divided by f of z. So this means g of z will be equal to f of z multiplying capital F of z. And also from our law of differentiation by product, we're going to have f prime of z to be equal to f prime of z capital F of z. We're going to have g prime of z to be equal to f prime of z capital F of z minus f of z plus rather f of z capital f prime of z. Now, suppose n1 and n2 are the numbers. Suppose n1 and n2 are the numbers of zeros for f of z plus g of z and f of z respectively, and also suppose the two functions have no poles. Suppose they don't have any pole, then n1 will be equal to 1 over 2 pi I integral of the curve contour f prime of z plus g prime of z divided by f of z plus g of z dz. And n2 will also be 1 over 2 pi of I integral of the contour f prime of z divided by f of z dz. From this point, the difference between our two numbers of zeros, n1 and n2, is going to be equal to, I'm going to subtract this from this, so we are going to have 1 over 2 pi I integral of f prime of z plus, now we have this f prime of z and g prime of z to be equal to all of this, so we're going to substitute it here. So we're going to have f prime of z capital F of z plus f of z capital F prime of z, all divided by f of z plus, instead of having g of z, we now have this, we have f of z capital F of z dz, then this is minus 1 over 2 pi I integral of the contour f prime of z divided by f of z dz. So from here, n1 minus n2 is going to be equal to 1 over 2 pi I integral of the contour f prime of z into, we are going to factorize f prime of z outside, we are going to have 1 plus capital F of z plus f of z capital F prime of z, or divide by, so the same thing for our denominator, we substitute f of z outside, and if we do that, we are going to have 1 plus capital F of z Then this is what we have here, and this is the z. This is minus 1 over 2 pi I integral of the counter f prime of z divided by f of z dz. So we are going to move to the next page. Alright, so from here we are going to have n1 minus n2 to be equal to 1 over 2 pi I integral of the counter. Now we are going to split this integral here. So the first one we're going to have f prime of z into 1 plus f of z divided by f of z into 1 plus capital F of z dz. It should be plus 1 over 2 pi I integral of the counter of this second part f of z capital F prime of z divided by f of z into 1 plus capital F of z dz minus 1 over 2 pi I integral of the counter f prime of z divided by f of z dz. So n1 minus n2 will be equal to 1 over 2 pi I integral. Now we have this to divide this. We have f prime of z divided by f of z dz plus 1 over 2 pi I integral of the counter f of z will divide f of z, be left with f prime capital F prime of z divided by 1 plus f of z dz. This will now be minus 1 over 2 pi I integral of the counter f prime of z over f of z dz. So from here you discover that this, we subtract this, you now have n1 minus n2 to be equal to 1 over 2 pi I integral of f prime of z capital F prime of z divided by 1 plus capital F of z dz. This can also be relating at 1 over 2 pi I of f prime of z into 1 plus f of z square of minus 1 dz. From our knowledge of Maclaurin series, we have 1 plus f of z raised to minus 1 to be equal to 1 minus f plus f squared minus f cubed plus f4 plus dot dot dot. That is what we have. So substituting this into this formula here, we're going to have this to be equal to 1 over 2 pi I integral of the counter of f prime of z to be into 1 minus f plus f squared minus f cubed plus f raised to power 4 minus dot 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 to infinity, and this is the z. This n1 minus n2 technically will be equal to 0. Okay, let's look at this. We have a curve, it's a circle. You take your movement from here. You take your movement from here. You move all around, and you come back to the same point, which will become 0. You come back to the same point, that will become 0. So by the time you integrate each part, you integrate all, coming back to this same point is going to give you 0. So the whole of this turns to 0. And this is our proof for the Rouche's theorem. Please like this video, subscribe to this YouTube channel, and don't forget to hit the notification bell to get notified each time we upload a video. Thank you.